My name is Nicola, aka Socrates, and you're watching Singularity One-on-One. If you guys enjoy this show, you can help me make it better in a couple of ways. You can go and write a review on iTunes, or you can simply make a donation. Today, my guest for the second time will be Dr. Michael Fossel. If you guys have not done so yet, please go and see our first interview, which we did in Michael's lovely garden in Michigan, and where we discussed aging in general. Because today we would actually dive into the specifics of his fantastic recent book, the Telomerase Revolution, that I just finished reading. So welcome, Michael. It's nice to have you back on my show.
Thanks, Nicole. Thanks for having me.
Fantastic. Excellent. So, Michael, I know your time is very valuable, so let's just jump right in. What is your book, The Telomerase Revolution, all about?
It's about a new way of looking, or a slightly altered way of looking at how aging works and the implications for human disease. And essentially, because we look at the process a little better, a little more sophisticated way, it gives us a much more optimistic and I think realistic view of what we can do about age-related diseases like Alzheimer's and heart disease.
So you say slightly more optimistic and slightly more realistic. How is that even possible?
Well, let me give you an analogy. Let's say that we went back to the early 18th century in Europe, and we were trying to deal with smallpox. And all we had were herbs, herbal preparations, different things you could drink, and roots, fungal preparations. And we were disappointed because none of those worked. Well, the problem is not that people aren't working hard at things like that. The problem is they're not viewing the disease properly. And now, throughout history, actually, India, China, Turkey, there have been examples of people treating smallpox or preventing smallpox, cowpox. But finally, in the late 18th century, Jenner published his results, and it became kind of clear that you could do something realistic and optimistic about smallpox. So again, the problem, I think, with Alzheimer's is much the same. It's not that people don't work hard and think about this, but their understanding of what's going on and how to approach it is wrong. And as a result, you get both an unrealistic and a very pessimistic view of what you can do for Alzheimer's. Once you look at it differently and ask, how does it work? Again, as we do with smallpox, once you change your mindset, you begin to realize that, in fact, you can do something about these things.
Fantastic. So before we jump into the nitty-gritty details here, let me ask you, what is your general goal? I mean, last time when we spoke, you said that you'd rather go and cure Alzheimer's instead of writing another book on the topic or another science paper. And yet here we are, we're discussing your latest book on the topic.
Well, I confess that the book was already pretty much written by the time you and I talked last, and it's finally come out. Now it's coming out in some 6 languages and beginning to have a hard time keeping track of them. And as you probably know, the Wall Street Journal said it was one of the best science books of the year. Got a glowing full-page write-up in the London Times. But as I said to you then, and as I say now, writing books doesn't cure disease. If you can change somebody's mind, get them to work on things, that helps. And in fact, the book has helped. Somebody called me the other day who read my book twice. He's a real estate developer in San Francisco who wants to put together a very large fund to have us continue this work. Well, in that sense, it helps, but it's the work itself that matters. It's the curing disease, not talking about it. I give you another example. As I may have mentioned to you before, the Nobel Prize for telomerase work really came out now 7 years ago. Good work, very studious, very academic, but by itself, it doesn't cure disease. Same thing. You need to actually do the work, not talk about it, not simply do bench research.
And I remember you even said back then, and of course, I kind of gathered that most of the book was written because actually, as I was reading the book, I kept noticing lots of things that you said during the interview that you've written about in the book. So that was kind of a pleasant surprise, if you will. But one of the things that was both in both of those was that you said, quote, "I don't want to understand aging. I want to treat aging."
To treat aging, I think we need to understand it. But the point is not an academic understanding. The point is clinical outcome. And it reminds me of what I used to talk about when I deal with residents, medical residents, for example, at my hospital. And they come in because I was their professor, and they would emphasize finding the diagnosis. Well, patients don't come in for diagnosis. They come in to be made better. And it is generally true that knowing the diagnosis helps you make patients better. but the diagnosis per se is empty. It needs to be, you need to do something with it. And the same thing here. The point is not, can I understand aging? To me, that's what I think of as beer conversation. Happy to talk about why aging works and how it works sort of over a beer, but the nitty gritty, the concrete is, where does it take you? Does it make people's lives better? And the answer is, I think it can. Now, I think we do need to understand aging to get there, but the understanding aging by itself is not the point.
Right, and actually in your book, you describe this as the fact that if you want to get somewhere, you need both a map and a ship. So the question then is this book kind of the map?
Yes, it is, and it's helping me actually get the ship as well. You know, the ship in some sense for me is the technology that lets you do this. For example, now 15 years ago, I was offered a very large amount of money to take this to translational work. We didn't have some of the parts of the ship right then. It's a lot easier to do this now for human patients than it would have been in 2001. The map, in my mind, has been around for 20 years this year. A little longer, actually. I published the first book on this topic 20 years ago, but you know, it's about time we set sail.
Yeah, fantastic. I totally agree with you that it's about time. But let me ask you probably the last sort of general question about the book. How will you measure the success and failure with this book? In other words, as you like to say, what's the data say so far?
Well, you know, the book itself, who was it? Was it Oscar Wilde or something one time said that anyone who writes a book for any other purpose than making money is an idiot. Something like that, except he said it in a very humorous way. And if you want to measure it in terms of sales and money, the answer is, okay, you know, I've gotten great reviews. A lot of people seem to like it, but, you know, but that's not my measure. When I see that people have read it, understand, want to invest, want to push this, that to me is a better measure of success. So the book to me is in some ways a vehicle. And to the extent that it helps me take this to clinical work and human trials, that's the success.
And actually, let me throw in an audience question here, submitted by Daniel Lemire, if I pronounce his name right. And he says, how does Michael feel about the sometimes negative reviews he got regarding the vision offered by his book?
About what vision offered the book?
Negative reviews.
About this book or 20 years ago? Because 20 years ago, a couple of people who won Nobel Prizes, who will go unnamed, actually said it should be banned, which I find kind of funny. I think it's a recommendation. Not many people have people want to ban their book. And these are the same people. When I said 20 years ago that it could probably have an impact on human aging and age-related diseases, they said that it was an insult to science and my book should be banned. These people are now saying the same thing themselves. All right. Again, I find that kind of funny, kind of puckish. But you know, the only reviews that I've seen negative on this book so far, the new one, and maybe I've missed a bunch. One person was mad because some people I know wrote reviews. Well, I'm sorry, you know, family members and friends sometimes do write reviews. I can ask them not to, but sometimes they do. The other was, I remember one person who complained vociferously because Amazon.com sent in my book and it came wrinkled. Well, I'm sorry, I didn't do that. It was not my fault. I'm sorry it was wrinkled, but you know, that doesn't make it a bad book. And then there were some odd ones. There was a review in an unnamed UK paper that came out just a couple of weeks ago. And what the person said was that they didn't really want to live longer. It would be horrible if people did because they'd watch their children die. So how's that different than what we have now? It sounds like what you're saying is you prefer to die young and with a lot of disease rather than live longer and be healthy, in which case it's your choice, but it's kind of an odd one from my perspective.
Yeah, I had a similar argument yesterday with someone in preparation with your interview. And my response to their kind of similar claim was like, why don't we say the same thing about vaccines or, you know, antibiotics or heart surgery or any other, you know, life-saving treatment? You know, why don't we just forget about medicine and let everyone die from, quote, natural causes then?
And people are welcome to do that if they want to. To me, it's, you know, now let me put it more carefully. I mean, if you said to me, here are your choices. You can have Alzheimer's and spend 8 years in the nursing home slowly dying, or you could have Alzheimer's and live for 20 more years with Alzheimer's nursing home, I'd say, no question. I'm not interested in the other one. I'm interested in minimizing my time being unable to care for myself in nursing home. But that's not the question. The question is, would you rather have 8 years, which is mean time to death and diagnosis of Alzheimer's, and spend your last few years in nursing home, or would you rather be healthy, able to play tennis, talk, find your car keys, remember your name, tie your shoes, feed yourself? Yes, I'd take that. And that, frankly, is what we're talking about. I mean, if we're from theoretical considerations and looking at the animal data, we're not talking about extending the lifespan slightly with Alzheimer's. We're talking about reversing Alzheimer's. Let me be specific on this one. The darling approach for the last 10 years really has been monoclonal antibodies, dealing, for example, with beta amyloid. Certainly not the only approach by a long ways, but it's been the darling. And in July 22nd of this last year in Washington, an unnamed major pharmaceutical company came out with the results of their unnamed, I'm not going to mention here, product, and it's a monoclonal antibody. And if you look at the curves of what happens, this is me slowly going downhill with Alzheimer's disease, and I get worse and worse, and finally die. And here's the curve once I add the monoclonal antibody. That it shifts slightly up, but it's the exact parallel course. The vector's the same, the outcome's the same. If you look at the step off, the argument is that you've delayed it slightly in early Alzheimer's, but after that, everything goes straight downhill exactly the same way. And the statistical argument is that you've delayed it. If you look at the measure of that, it works out to about 3 months. So what they're saying is we can extend your lifespan in the nursing home by 3 months over an 8-year period as you die of Alzheimer's. This is like, last year I had to give a course, which was a lot of fun, on Ebola. The mean time to death on Ebola is about 7 days. And this would be like me saying to you, Nicola, I can't cure Ebola, but I can give you a brand new product. It's kind of expensive, but it'll extend your lifespan by 5 hours. That's the ratio, 5 hours. I'm not impressed, particularly if that means, in the case of Alzheimer's, I have 3 more months in the nursing home. What we want to do is not take these curves and have them go downhill like that and bump it slightly. We want to make the curve go like that. We want to bring it back up again. And that's exactly what we can do in animals. Whether we can do it in humans or not, I don't know. But I do know we're going to find out.
Mm-hmm. Yeah, okay. So it's time for us to jump into sort of the meat of the matter here. So let me start with asking some more specific questions. For example, how do we age, Michael? Or in other words, what is the so-called telomere theory of aging, and how is it different from all the other theories that came before it?
Well, I'm going to make some bold statements here. It's different because, one, it's consistent with all the other partial theories of aging, and two, it's supported by the data. Not only the data to date, but experimental or interventional data. That is, when you do what should make a difference, it does. But the difference actually, again, it's a different paradigm in the way people usually look at things. Let me see if I can come up with an example. I'll take the example actually of Alzheimer's disease, aging within the nervous system. The standard assumptions go something like this. You've got a neuron, and it's surrounded by a number of other cells, glial cells. And as time goes by, the beta amyloid forms microaggregates and plaques. And as this increases over time, that damages the neuron, and the neurons finally die. You clinically have Alzheimer's, which I see clinically. But the problem is they're treating that beta amyloid, the microaggregates, for example, as a more or less static pool. That is, there's a pool of beta amyloid, and it slowly gets denatured and cross-linked, and that causes problems. But in fact, that's not a static pool. It's a dynamic pool. Beta amyloid is always being produced and destroyed. So this is a dynamic pool. And I'll give you an analogy about this. Let's say that you and I recognize that anytime we look at 1,000 people, some of their cell phones don't work. Okay, and we're trying to predict what's the major predictor. Well, if I were thinking about beta amyloid the way most researchers think about it, I would say it must be genetic. That is, the difference between whose cell phones fail and whose don't is whether you have an Android or an iPhone or whatever the brand. And to some minimal extent, I'm sure that's true. One or the other must have a slightly higher fail rate, just like ApoE4 has a slightly higher fail rate than ApoE2. But that's not what predicts whether your cell phone's going to die. What predicts it is how long have you had it. Pretty much pure and simple. And there is a turnover of cell phones just the way there's a dynamic turnover of beta amyloid in the nervous system. So a typical cell phone in the United States up until now, or actually many places in the world, has a 2-year contract. That's the turnover rate. The failure rate at the end of that time is a couple of percent. Phones fail in any population. What happens if I slow down the turnover rate and give you a 20-year contract? The projections are that your failure rate of cell phones will be up around 89% because cell phones just don't last that long. So the predictor for whether you're going to have a cell phone failure is not the brand, it's the time you've had it. The predictor for whether you're going to get Alzheimer's disease is not your allele, beta amyloid, your ApoE4, ApoE2. It's not the gene, the allele that you've got. The predictor actually is the rate of turnover of the beta amyloid core. And if you look at what happens with the cells that control that, the microglia, what you find is that their ability to bind the beta amyloid goes down with age. Their ability to internalize the beta amyloid goes down with age. Their ability to degrade, the enzymes that they produce, the numbers of them, to break down beta amyloid go down with age. And if you turn those around, it goes back up again. So the problem is with a lot of Alzheimer's researchers is that they're so focused on, as it were, the brand of cell phone that they're ignoring the length of the contract. And that makes all the difference.
Mm-hmm. Very interesting. So let me read a quote from the book where you basically also give the gist of the theory in a single sentence, where you say, the telomere theory of aging can now be put in one sentence. Cells divide, telomeres shorten, gene expression changes, cellular repair and recycling slow down, errors slowly accumulate, and cells fail.
Correct. And that's just exactly what I was saying with regard to beta amyloid. Now, some people, we still tend to call this the telomere theory of aging, and we're stuck with it. More appropriately, we probably ought to call it the gene expression theory of aging, or the epigenetic theory of aging, because what you're looking at is a change in gene expression. And I don't care. I don't really care what you call it. I don't really care the long pathology, the cascade of what occurs. What matters to me deeply is a single question, which is, where is the most effective single point of intervention? Never mind what causes it. If I ask you about Ebola again, you're going to have Ebola. The question is not what are all the various things that happen within what cells in your body that cause it, because it's very fascinating. There's a lot of interesting pathology. The question is, where is the effective point of preventing it or curing it? And the answer is vaccination, immunization, actually. And the same thing pertains here. The question for me is not that long sentence, which is true, but where in that sentence do I make a change that's not only clinically most effective, but for that matter, financially most effective? I don't want to waste a lot of time, money, or people's lives. I want to get in there and find a way to fix things quickly, easily, fastly, efficiently. That's what matters.
I know that this is kind of a very ignorant question, but tell us why the difference of the intervention point. For example, in Ebola, it's vaccination. Mm-hmm. And why don't we have a vaccination as the most efficient intervention point for Parkinson's and Alzheimer's and anything? Can we not develop, in other words, a vaccine for old age? Why or why not?
Well, not in the technical sense of it being a vaccine, but as it turns out, in the same sense, let me put a parallel here. You could have small molecules or you could have biological molecules in treating Ebola. And small molecules don't work. Biological approaches, that is, immunizations, do work. The same thing, in a very rough sense, is true about age-related diseases. You can go after things with small molecules, or you can, and it will affect a certain amount of gene expression, or you can go after them with biological molecules, which have a different level of intervention and will prove more effective and do in the lab so far. So the question still is, where do you intervene? I'll give you another crazy example. Say I take the case of heart disease, all right? Here you are, you're 75, you've got a family history of heart disease, you've got high cholesterol, you have high blood pressure, you've got a slightly high blood sugar, you're a smoker, and you want to know, how can you make sure you don't die of heart disease? Well, I can think of a lot of interventions. Stop smoking, lower your blood pressure, lower your cholesterol, take up exercise, change your diet. We can go on and on. Or I can put you on statins. I can give you a coronary bypass graft. I can give you a stent. I can do a heart transplant. Well, those are all, in some sense, interventions. Some are more costly financially. Some are more costly in terms of side effects, risk, death than others. Some are simply not very effective. Some are painful. A lot of people are not willing to change their diet. It's not really painful, but they're not going to do it. So there's this whole gamut of interventions. And the question there, again, is, where's the most effective point of intervention? Well, I think the most effective point of intervention is to use telomerase to reset gene expression in the endothelial cells, which is where the disease cascade starts. And we'll prove it soon. But you see, that's still the key question. And we need to come up with a key answer, which is what works best.
And again, I'm very ignorant about this. I apologize, but why can't we accomplish that with vaccination?
Well, I'm not sure how you could. Again, to take the case
I'm just trying to, when you don't know anything, it's easy to imagine the answer.
I feel that way about most things in life, actually. Particularly after I used to have night shifts at the hospital. I felt that way about everything. Generally, what you're looking at with an inoculation for something, an immunization for something, is you're trying to teach your body that the next time you see this invader, recognize it and kill it. Again, putting it simplistically, but that's kind of true. There are these two parts of the immune system, the innate immune system and the part where you learn in the immune system. And you're trying to take that second part of the immune system and educate it and say, don't let that happen again. Next time you see Ebola come by, don't let it kill you. Now, that same sort of approach doesn't help when what you're dealing with in aging is not a viral infection or a bacterial infection or fungal infection or chlamydial infection. No, what you're dealing with is a gradual change in the pattern of gene expression. And that's the key. So the question is, all right, you've changed my gene expression. How do I get it back to where it was? The analogy I sometimes think of is, the difference between the cells in this finger and the cells in my cheek is not the genes. There are some cells in my body that have different genes, particularly in the immune system where there's some odd things going on. But in a sense, all the cells in my body have the exact same genes. But the difference between my finger cells and, say, my cheek cells is not genes, it's the pattern of expression. The same thing is true of aging. The difference between my cells at age 6 and my cells now at age 65 is not that I have different genes. It's not even that I have a different pattern not that I have damaged genes. I still produce quality proteins, for example. The problem is the pattern of expression has changed. And with regard to the proteins, it's not that I produce bad proteins. I just don't produce them as fast anymore, don't turn them over as fast anymore. And the outcome is age-related diseases. A classic example would be my skin. If I look at what happens with aging skin, a lot of changes happen. But let's look at just two proteins. Two classic proteins that lie between most of my cells here are both collagen proteins and elastin proteins. And the collagen provides some strength, and the elastin provides, not surprisingly, elasticity. And as I get older, what you'll find is that the skin, when you pull it up, doesn't snap back as fast. The young person goes right back. Very old person goes up, tense for a while, goes down very slowly. Well, the problem is not that 95-year-old man doesn't make good elastin and doesn't make good collagen, but they don't make it very fast. They don't break it down very fast. And as a result, it's like the cell phone turnover. You got a 20-year turnover. A lot of it goes bad because it gets damaged. If you reset that to the 2-year program, as it were, for cell phones, if I could reset that on my skin, I turn the proteins over faster, and you'd end up not having the same wrinkles, loss of elasticity, so on. But that sort of problem is going on throughout the body with aging, and it always has an impact on age-related diseases. Mm-hmm. And I can't fix it with an immunization.
I see. Okay, so let's move on then. So in your book, you say in one place, and actually you generously published a couple of chapter excerpts on my blog, which were very popular, by the way. One is called Why We Age. Why Do We Age? So in that excerpt, you say that our bodies age on purpose. So can you perhaps unpack this for us and in general talk about why do we age?
Okay. Let me say again that, my concern is not why we age. The sort of the teleology of it. Why do organisms age at all? I sort of don't care. On the other hand, people ask, they want to know, and it's a good question. And let me say that it's hard to defend any answer you come up with because what experiment are you going to run to prove it? However, I suggest that probably we age on purpose, and it has to do with the rate of adaptation to changes in the environment. Right now, many people are concerned about global warming. Well, changes in global climate have been dramatic in the past 4 billion years. If you look at, for example, oxygen concentration, temperature of the planet, pH of the ocean, calcium concentration, you name it, it's changed dramatically. CO2. But again, not meaning to make light of climate change, but I want to put it in perspective. Our organisms over the past 4 billion years have had a lot bigger fish to fry than a couple of degrees centigrade change. No, I mean, there have been dramatic changes, things that result in death of a lot of organisms. Again, ignoring getting hit by asteroids in the Chicxulub meteor crater. No, and of course, the biological environment changes too. That is, if I'm some little forest creature and a competition moves in, it changes my biological environment as well as my geological environment. So what organisms need to do is to be able to adapt. If I'm in an environment that never changes geologically or biologically, I can afford to be a long life individual. I could be a brontosaurus. I could be anything with a long lifespan. Wouldn't be a problem, or a human being. But in any environment that calls for rapid change, either because of prey, predators, again, competition from other species, your own species, geological changes, anything like that, there's a premium put on short lifespans because it gives you faster turnaround time. It's sort of like having a car that can turn quickly versus a big truck that takes miles to turn well. The faster you can turn around and adapt, the more likely you are to survive. So, for example, bacteria that have very short lifespans tend to do very well because you change the environment, adapt pretty quickly to things. For example, antibiotics, which is a problem. And here would be an example of that. Say we had two populations of deer, for example, on two islands. They were identical except that one had a longer lifespan than the other. If I change the environment, I increase the environment 10 degrees centigrade, over time, the shorter lifespan group will be able to adapt more quickly than the longer lifespan group. So it's simply a matter of basic evolution. And evolution is always sort of a truism. To put it bluntly, the theory of evolution basically says that things that survive, survive. Well, shorter lifespans, if you change the environment, survive. Now, it turns out that it's more complex than that because it also has to do with things like cancer or mutation. Most of us regard mutations as horrible, evil. Well, if they're your children, they are. But you cannot afford to have a species that has no mutation rate if the environment's changing, because then they continue in a straight line, the environment takes a curve, and you've got a dead species, an extinct species. So there's a value in mutation. The question is not only do you have enough mutation, but can you alter the rate of mutation to match the change in the environment? And that's where cell senescence turns out to come in a very roundabout way. Basically, you need an organism that can alter its lifespan and its mutation rate to adjust to the rate of biological or geological change around it. Complex, but probably true. Who knows? I could be wrong.
I don't get too many interviewees who say halfway through their sentence, I could be wrong, by the way.
Well, it's always true of all of us, As I always say to my students, theory is one thing, data trumps theory every time.
Yeah, that's one of my favorite quotes, actually, from you. And I think I have it somewhere later on, but let me see if I can't find it right now, but it's one of my favorite quotes from your book where you say that guesswork is useless, logic is better, and data is best.
Yeah, I remember a scientist friend of mine who once said there are no such things as UFOs. I said, well, can you prove it? That's theory. I'm not saying there are or aren't UFOs. I'm saying that's theory. If you show me one, I know it's there. If you don't show me one, all I can say is I haven't seen one. The same is true of ghosts and telepathy and anything you want to say. A true scientist wouldn't say they don't exist. They'd simply say I haven't seen one yet. And I think the same thing is often true in medicine. I'll give you a far out example. If you could show me that you could use a blue crystal pyramid to cure malignant melanoma, if it works, it works. Even though I would regard it theoretically as complete nonsense. The question is, does it work? And that's true of so many things. I remember seeing this with regard to things like chelation therapy. You'll find people who believe in chelation therapy for everything, and then you'll find standard physicians who say it never works for anything. And yet, there are a number of heavy metal overdoses that are treated with chelation. So what they should be saying is, yeah, it works here, but not there. Fair enough. But go with the data, not your theory. Or the other example I've sometimes given is herbal medicines. You'll find people who think that herbal medicines are always safe, and yet I can give you easily a concoction of foxglove tea that I grow in my garden, and you'll be dead quickly. Or you'll find physicians who will say herbal medicines don't work ever while they're drinking coffee.
Okay, so let's move on again. In your book, you're talking about the difference between what you call direct and indirect aging. Can you please explain that distinction for us?
Sure. In some cases, here the classic example would be osteoarthritis. In some cases, if I have a disease like osteoarthritis, The problem is the cells that line the joint itself, the lining joints, are called chondrocytes. And those cells divide, they age, and the result is osteoarthritis. So the cells that are doing the aging are the ones that show the disease. In other cases, the problem is not with the cell that's doing the aging, it's the innocent bystander. So for example, many people die of heart attacks. In fact, most of the audience, left to its own devices, if we don't get around to changing anything, the majority of the audience right now will end up finally dying of vascular disease, vascular aging. So if you die of a heart attack, typically what's going on is that the coronary arteries have had a blockage, and the result is you didn't get blood supply to the heart muscle, and the heart muscle died, and therefore you died. But the heart muscle is the innocent bystander. Heart muscles essentially show no aging changes. Muscle cells, roughly speaking, don't divide. They do about 1% a decade, but roughly speaking, they don't divide. They don't show cell senescence. They don't show problems. The problem occurs in the vascular lining. And so what you've got is an indirect kind of aging. The vessel, the endothelial cells lining the vessels age, and the result is they end up killing the perfectly innocent bystander, the cardiac muscle, and you. The same kind of indirect aging goes on in the central nervous system. We've focused now for a century on neuronal cell death as underlying Alzheimer's disease. And yet, it looks like the neurons, the innocent bystander, it's the microglia and perhaps the astrocytes that are responsible for the changes that result in this cascade of pathology. And at the bottom of the avalanche is that poor neuron.
Very interesting. So now you also have kind of two chapters on, one is on slowing aging and one is on reversing aging. So let's take it step by step here and start with slowing aging. What can people do now to optimize health and longevity?
Nothing very sexy, mostly. Mostly it's things that we all know about and we don't do. So for example, if I want to increase my rate of skin aging, all I have to do is go out and get a sunburn. If I want to increase my rate of cardiovascular aging, all I need to do is take up smoking. So we're well aware of a lot of things that have an impact on the rate of aging of various systems. And it really is rate of aging. It really has an effect on lifespan. Or in a more sort of prosaic way, fasten your seatbelt. It has nothing to do with your biology, but it sure has an impact on your chances of death. So there are a lot of things like that: diet, exercise, not living in Syria right now. Any number of things that we all know that we could or should or would like to do that would make our lives healthier and longer and better. And in some sense, those slow aging. Certainly the diet, the exercise, the exposure to sun and various toxins like tobacco that can affect aging. The others are just a stochastic thing, going to war zones, not wearing seatbelts. Stochastically expect lifespan, but not really aging. But still, those are all known to us. People generally don't do them. Now, if you want to ask, is there anything that's more interventional that would affect aging? There have been a lot of claims over the years. And most of those claims have no data. They're interesting, but no good data on them, at least in human studies. The only ones I know that there is some relatively good supportive data for is the use of telomerase activators. There are two studies, one published 2011, one published 2013, that suggest that these have an impact on the actual rate of aging as measured by a number of biomarkers. But that doesn't mean they suddenly take somebody 70 and make them 30. It just means that there's some hints in there, something's going on. So that's a possibility. One of the problems with those approaches is that they tend to be expensive on the market. And the cheaper the version out there on the market, the less certain you are that you're getting something that's an actual telomerase activator. And there's a lot of uncertainty. So hard to say. So if you want to slow aging, the answer is you probably should be doing what you know you should do anyway that you're probably not doing. And I don't have much better for you that isn't either expensive or unknown and unprovable yet. That's different than what we're about to do, though, which is that next chapter where you're going after this.
Yes, absolutely. But before that, I want to say that on that chapter, what impressed me is that you give kind of a very sort of a common sense advice, if you will, and you even mention our grandmother's advice. And you end up by saying three words that I took away from that chapter, which is eat your age.
Yeah. One of the problems that people have is that, as I say, the protein pool turnover, metabolic rates in general slow down with age. So at age 20, never mind whether I'm exercising or not, just even with a basal metabolism, I've got a higher metabolic rate and turnover at age 20 than I do at age, say, 70. So I can, in a sense, afford to eat more food when I'm 20, but I also need it more because I'm rebuilding proteins, turning over all sorts of molecules on a daily basis. As it were, the cell phone contract is 2 years, so it costs more money. The money is food. If I have a 20-year contract, doesn't cost as much, the cell phones go to hell, but I don't need much food. You've kind of got the 20-year cell phone contract at age 90. And if you tried to eat the same you ate at 20, you wouldn't be a 20-year-old, you'd simply be a very fat 90-year-old.
Yes, indeed. Okay, so let's talk about the other chapter, which is on reversing aging. So can we do that, and how?
The quick answer is yes, and maybe both. The yes part of it is we know we can do it in cells. We know we can do it in tissues. We know that we've done it in a number of ways in animals. The question is, can we do it in humans? The answer is probably. That's why I put it that way. So let me be more specific. If I'm looking at human cells, we've now known, I mean, the first article on this came out in 1999, and it was a very turgid, hard to read article, even knowing the data. But what it showed is when you reset the length of telomeres and you reset gene expression, the cells acted like normal young cells. Okay. Then in the next few years after that, 2000, 2001, a series of little papers came out that showed the same thing in tissues. So the classic example is I take young skin cells and I put them and I grow them on an animal, and I get what looks like a young patch of human skin. If I do the same thing with old human cells, I get what looks like an old patch of human skin. If I take those old skin cells and I now reset telomere lengths and I grow them out again, I get what looks like young human skin. And the same is true of a number of other models, looking at bone, looking at vascular tissues and so forth. So we have, in a sense, known that we can reverse aging in cells and tissues now for about 15 years. Then there were those 2 human studies I mentioned with telomerase activators that were interesting, not definitive, but interesting. Hard to sweep under the rug, but not impressive either, just interesting. But since that time, there have been a number of interesting studies looking at mice. Example, Ron DePinto, when he was at Harvard, before he moved to Texas, did an interesting experiment with mice where he actually bred a variety of mouse where he had a telomerase gene he could turn on and off. Now, I can't do that with human patients. But what he found is when he turned it on, the animals, their behavior improved compared to old animals. They act more like young animals. A number of physiologic measures, bone mineral density, things like that improved. In fact, brain weight improves. So if you have a young animal, you look at the old animal, typically the older animal's brain has a weight of about 75% of the young animal's weight. But when you turn on telomerase gene, it goes back to just about 90% of normal young weight. What you've just shown is that you can essentially regrow brain tissue. And interestingly enough, it wasn't just brain tissue, but again, there were behavioral effects. It is behaviors of these animals were more consistent with being young animals than being old animals. Again, something inflected. Again, compare that to where the Alzheimer's trials, where things go downhill parallel, somebody's taken an inflection. The same thing was true of Maria Blasco's work, where she did something that we can do with humans. That is, instead of trying to breed mice, or as it were, humans, what she did was she used a viral vector to deliver a human telomerase gene, so she could essentially put telomerase, turn it on in her mouse cells. And when she did that, again, behavior improved, just any number of measures improved in these animals. For example, if I measure their ability to walk across a tightrope, old animals can't do that very well. But when you put on telomerase, they can do it just as well as young animals. Interesting. What are the implications of that for Parkinson's? What are the implications of that for Alzheimer's? What are the implications of that for ALS? Interesting question, isn't it? So we know that we can reset some very remarkable things in the brain and also in the vascular system, which you didn't mention in the ones. The question is, again, can we take that to human beings? And the answer is we now have, back to the ship and the map we've got for 20 years, we certainly have everything we needed outfitted in the ship. We're ready to go ahead with human trials.
Fantastic. So before we start discussing the human trials possibility, let me say, I actually just found that quote that I was missing before, and I think it's from this chapter because you say, quote, "As in science, so too with advice. If you want the truth, then guesswork is worthless, logic is often good, but data is always best." End of quote.
Sure.
And let me throw in a question that would return us back to the those products that you mentioned already available on the market. It's a question from Ralph Wooden, who says, are supplements capable of lengthening telomeres? What are the adverse side effects, and what's the cost?
Well, first let me ignore all the unknown supplements. For example, we're not talking about vitamin supplements, mineral supplements, and so on. We're talking here in this discussion specifically about telomerase activators. And the group that's best known and best available commercially are a group called astragalosides. And it is clear that they can reset telomere lengths, and it is clear that they can do that in humans to a degree. And it's clear that it's got some very interesting effects, as I say, in humans. For example, lower blood pressure, lower blood glucose, better insulin control, better bone mineral density, just a better function of lymphocytes, goes on and on. Again, dramatic, but significant. There's something going on. Now, the first question would be, let me touch the little one first, little because it's easy to answer, which is cost. You know, the cost of these things typically runs several $100s a month if you're taking sort of recommended doses. Now, you've got options. You could say, never mind, I'm not going to take it. You can say, I'm not sure the data really supports it. Why would I waste my money? You could say, I believe the data. I think it really does work, but I don't have my head, can't do it. Or you could say, it's worth the bet and I've got the money. Some people would do that. The other option, as I alluded to already, is you can look out on the internet and you'll find a lot of sources of astragalosides. The problem is a couple. The major one is that you don't know who these people are. If they're providing a real astragenol compound, for example, other astragalosides, you're not sure. And we know there have been reports of some of these that have been lab tested and found to be false. There's nothing in them that's active. Now, that doesn't prove that some of them aren't perfectly active, legitimate compounds. The problem is, I, as a consumer, can't tell. I don't know. I have to take them down to a local lab, pay money, you know. So it's not an easy, it's a quandary. You know, do I get it cheaply and not know what I'm getting? Do I get a more expensive one that appears to be pretty well supported? That is, in this case, you know, the classic example is TA Sciences. They started this. They owned it. They bought the patents from Jaron, and they have more credibility in the market than most do, but they also have higher expense. So what do? That's still a tough question for the consumer. That's the easy part. Now let me get to the other interesting part, which is what about side effects? And the quick answer is probably none. But let me be a little less facetious about that. The question that always comes up is cancer. You know, 20 years ago, I wrote about this in the first book that came out. I remember Judy Campisi's classic statement was the double-edged sword. And the idea was that if you had telomerase, it would cause cancer, but it might decrease aging. But if you don't have telomerase, you'll age, but you won't get cancer. And as it turns out, like a lot of things, that was simplistic. And in fact, a lot of it was wrong. First of all, let me say that telomerase doesn't cause cancer, period. It acts as one of three permissive steps within cells. And there are at least two steps outside of cells. But within cells, there are at least three steps. There's gene repair. If you get good or bad gene repair, because if you don't have good gene repair, which goes down with cell aging, by the way, you'll end up with more mutations and more risk of cancer. The second is called the cell cycle breaking system. And what happens is the cell looks around to see if there's gene damage. And if there is, it won't divide unless that breaking system fails, in which case, another permissive step going by. The third permissive step is telomerase. That is, if the telomere is short enough, the cell refuses to divide. Essentially, it acts like an old cell and says, I'm just too tired. I'm not going to divide. And if you put in telomerase, therefore, it will divide. So a lot of people would worry about cancer. Reasonable thought, but as I say, one, it doesn't cause cancer, it's only permissive. And two, the data actually don't support it in two senses. One is the theoretical sense, by the way, is we know that telomerase is a gene stabilizer. That is, you increase the stability of the genome. And one of the reasons is it turned up the expression of the four families of DNA repair enzymes. So your DNA is less prone to mutation. It doesn't affect inherited mutations like a BRC, one gene or something. But it does affect the rate of repair very nicely. So if I put telomerase in these cells, they tend not to mutate. They don't become malignant. Very nice. Here's the complexity. The complexity is if I have long telomeres, I've got very stable genes, I don't have mutations, I tend not to get cancer. If I have very short telomeres, I have increased mutation rate, but the cell refuses to divide because it's just too short. The telomere every time you try to divide, the cell just doesn't divide very well. But if I have a very short telomere and a high mutation rate, and I increase the telomere length just a tiny bit, I might allow it to divide and therefore increase the risk of cancer. That's a narrow window. If I can increase the telomere long enough, what I do is I increase gene stability, increase gain of repair, and I lower the risk of cancer. But there's that little window you wonder about. Well, the data suggests this, and there isn't great data, but there's some data. The data suggests that, in fact, overall, the risk of cancer goes down with telomerase activators or with use of telomerase in general, except if you have certain animals that are prone to cancer in the first place. So the quick answer is the side effects in general don't exist. The side effects as far as cancer go are probably very small, if significant at all, but there may be cases. There may be that little window where things are just wrong enough. So interesting question. It's one of the reasons, by the way, that we're going to go after Alzheimer's disease. Because let's say, this is not true, but let's say that we knew that 1 in, 10,000 patients you gave telomerase to got cancer, okay? If I said to you, Nicola, you're getting wrinkles, I think I can fix your wrinkles, but 1 in 10,000 cases you'll get cancer, you'd say, never mind, I'll keep your wrinkles. And you probably say that about osteoarthritis because you'd probably rather just get a knee replacement than take a chance on getting cancer. But if I say that to you about Alzheimer's disease, the response is, there's no other treatment. It's 100% fatal. I'll take the treatment. And again, without being facetious, I think that's true. Again, the mean time to death with Alzheimer's is 8 years. There is no effective drug on the market, period. No exceptions. I'm sorry. You can waffle all you want, but there's nothing else. So yeah, we can tolerate a little higher risk, and it's one of the reasons I'm going to go after Alzheimer's first. It gives us a chance to effectively cure disease, and we'll get a better assessment of what that risk is, if there isn't.
Mm-hmm. Joanne Hewitt says, Nicola, please send my regards to Dr. Fossel and ask him if he expected it to take so long to translate telomere-centered therapy.
Well, back 20 years ago this year, I estimated that it would take between 1 and 2 decades. And in fact, it took 11 years before there was a commercial product out, which was the first TA65, the astroglycosides that TA Sciences put in the market. So it took 11 years. But that still doesn't allow us to do things like treat Alzheimer's and so forth. So no, I'm disappointed. Frankly, I thought that in 1996, I would sort of tip the first rocks down the avalanche and people would get the work done. I've been disappointed, and it's one of the reasons I've decided it's time to do the work myself, because people just are not out there doing what they could do. And it's been interesting because suddenly things are changing. Not only do I see more in the way of research, even in academic centers, let alone people beginning to do more practical approaches, but the same is true in the biotech industry. I begin to see more biotechs interested in this. And I just got back from a conference in San Francisco, and I was delightfully surprised to find that I've got about a dozen VCs chasing me right this moment. We're talking about putting the money into this to take it to clinical trials. So yeah, it's about time. Way past time, actually.
We'll come back to that topic in a while, but let me ask you first this. Speaking of practical approaches and things changing, what do you make of Liz Parrish's experiment with gene therapy in general and telomere lengthening in particular?
Well, Liz and I talked about that before she did it, and I talked to her about what could be done and why. And let me say that here are sort of the trade-off. On the one hand, an awful lot of people, not everybody, an awful lot of people are upset with regulatory organizations because they slow down the rate of getting drugs to market, for example. On the other hand, if you get the drugs to market and it fails or has side effects or causes cancer, people are very upset that it came through. So, sort of, it's pros and cons.
Yeah, just a couple of days ago, 5 people in France had adverse severe.
Good example.
One went brain dead first and then died. The other ones are in critical condition. So it does happen indeed, which is why we have the slow process.
Or the classic thalidomide disaster, or the early gene therapy done 20 years ago, where kids just simply died. We all thought that, or a lot of people thought that it would suddenly be a panacea, and it's not. There are risks, and the gene therapies have improved dramatically since that time. Now you're beginning to see real successes rather than just risk. But there's always these trade-offs. It's not an easy thing. And when I see somebody like Liz, what I see, and a number of people like this, she is frustrated with the time it takes, and she wants to get things proven now. I agree. On the other hand, I want credibility. I like Liz. She's a personal friend. And I'm not associated with BioViva in any way. But I understand the frustration she's got. Here's the problem I see. Liz, never mind how old she is, I won't say that. But Liz at her age is pretty healthy. And let's say that what she's
actually just said in her interview that I did with her that she's 45, and it's about to come out. So
yeah, okay, good, because that's what I was going to say. Liz is about 45. But the problem is, let's say that what we talked about doing with Liz and what she did one of the things. She used a different gene as well besides telomerase. But let's say that worked absolutely perfectly, and it made her totally young and made her 20 again, and everything was absolutely flawless. People wouldn't believe it. They'd say, there's one person who did it, she probably made it. They'll say that. Never mind if it's true or not. That's what people will say. Because it's one person and she didn't go through the FDA and she didn't go through the right hoops. And fairly or not, justly or not, a lot of people will say that, which means it's harder to get that to market, even if she's dead on, absolutely right. It's hard to get it to market. So what we've decided to do is take the other approach, which is it takes too long, it's driving us crazy, we're frustrated, we'd like to move along. But one, in ascending order, and I want it to be safe. I don't mean it has to be perfectly safe, but it has to be, I don't want to make a mistake by doing something a little off. I want to be able to make that as safe as possible. Two, I want it as effective as possible. If I can increase the efficacy of this by doing something a little different, I want that to be done right. But the third is credibility. If I can show that I can take 6 patients, even 6 patients, in an FDA-sponsored trial, phase 1 trial against Alzheimer's disease, and reverse, even partly, reverse the cognitive decline, and do this with careful monitoring and careful oversight, I've proven my point. And there'll still be people who say, he must have made that up. But I'm sorry, I'm going to have the FDA looking over my shoulder, and I'm going to make darn sure that this is done in such a way that as fast as possible, we can then take that to market and say, let's cure all the people we know with Alzheimer's, rather than have them say, I don't know what really happened, I don't trust them. So I want to be able to fix these things. So I'm taking that pathway on purpose. I want it credible, I want it effective, and I want it safe so that people can use it, not just to prove the point, but to be able to get it out there where people get a chance to use it.
Yeah, and the other thing that you always like to bring is the data. So I want to ask you, what's the data that would prove or deny those results? What should be looking for? What do you want to test, for example, in Liz, in her samples? What are the biomarkers? Because to be honest, I didn't get specific enough answers during her interview to my liking, at least. And of course, I'm a nobody in that field. So I'm just wondering what's the measurement that you want to see pre and after, and then to maybe monitor on a daily or weekly, monthly basis to change that progression, to monitor that change of progression of whatever it is.
Well, let me make 3 points about that. The first is that, as I say, Liz is too damn healthy. If you took biomarkers on her, most of the time the answer is going to be they're normal anyway. They're nice, youthful, healthy biomarkers. So how can I get them better? Let's say, for example, that I were to look right inside her endothelial cells of the coronary arteries, I might find no damage whatsoever. So how can I fix that? What am I going to measure? It's already fine. So that's the risk, which is one of the reasons that I'd like to look at sicker people, because I'd like to show we can fix it, not just prevent something. And maybe Liz could show that we can prevent a heart attack or Alzheimer's disease in 40 years. I don't want to wait that long. I want to take sick people and turn them around. So there are 2 ways of looking at this. One is general body measures. So, for example, again, I can look at blood pressure, hypercholesterolemia. I can look at your insulin response, bone mineral density. I can a lot of things. Specifically, we're going to start out looking at Alzheimer's disease. And so there are specific sets of measures we're going to look at. And they fall into 3 categories. The first is imaging studies, for example, a PET scan or an MRI, where you're saying, oh, look at that. They've got some degeneration in their white matter, and we'll reverse it. Or the size of the ventricles, we'll reverse it. The second sort of measure are chemistry measures. And classically here, you're looking at lumbar puncture, for example, that is cerebrospinal fluid. But it can also be peripheral measures in bloodstream, where you're looking at things like microRNAs or various molecules that are associated with beta amyloid metabolism, or even in some cases with synaptogenesis. For example, back to the imaging, there are ways of actually measuring synaptic dysfunction on the basis of some tracers we can put in with an active PET scan. Okay, so you can look at imaging, you can look at chemistry, sometimes you can look at them together. But the other thing to look at is behavioral measures. Because if I were to say to you, listen, you can have your choice, Nicola. You can either have perfectly functional brain and your behavior is absolutely normal, but the scans look like hell and your chemistries are way off the wall. Or you can have perfectly normal scans, perfectly normal chemistries, but you can't tie your shoes, remember your name, or do anything to feed yourself. What matters to you is your behavior. The others are secondary. That is, usually they're biomarkers. They're biomarkers of my behavior. My concern is that I can remember my name, tie my shoes, speak a sentence, feed myself. Never mind what the doctor tells me about the imaging and the chemistries. I want to be me. So in a very real sense, for both patients and physicians, the gold standard in some sense is behavioral measures. The problem with them is they tend to be a little fuzzy. If I'm measuring your behavioral changes over time, I can look at any number of measures. There are all sorts of scales out there. So in some sense, they're the gold standard, but they're also, not as quite as objective in some ways. But they matter to everybody deeply and personally. So we'll be looking at all three. When we look at Alzheimer's, we want to look at behavior, imaging studies, and chemistries, all three.
Very good. Yeah, that's very good. So let me ask you, if we presume that everything goes perfect with Liz Parrish's experiment, would that in a way be a small, maybe statistically insignificant, but nevertheless a small practical example of your of the accurateness of your telomere theory of aging?
Yes, but again, with two caveats. One is that she's already healthy, so how can we make her better? And two is there's that credibility gap. People will tend not to believe Liz. Again, if Liz called me and told me that there was an effect, I'd believe her. But the FDA probably wouldn't. Most clinicians and researchers probably wouldn't. And whether that's fair or not, that's sort of human nature. So that's the caveat.
Yeah, one of the things we discussed with her was that she's already lost about an inch on her waist, and yet she's gained weight. So her fat,
muscle mass.
Yeah, so she's gained muscle mass and perhaps bone density and stuff like that, which was very interesting.
Mm-hmm.
Anyway, let's move on to a few other audience questions. So Callum Chase here asks, what are the odds of achieving longevity escape velocity within the next 20 years or so? Are you familiar with the concept that Aubrey de Grey describes on longevity escape velocity as the moment at the point at which every year going forward we will be able to extend human life expectancy by at least a year?
Aubrey is often a little bit wild, but he is also it doesn't have a good understanding of pathology and the genetics involved, and as a result, he's conservative. Let me put it this way.
Aubrey conservative.
Yeah, wow. but sort of by mistake. Let me put it this way. Right now, if you said, when did we land on the moon? You can probably look it up in Wikipedia, and rather than just say it was July of 1969, you could probably get it to the nearest second or microsecond. You could probably find that time. If I said, when did we cure polio? The quick and dirty answer for most people in the street would be 1954, if they remember it all. And the honest truth is, well, we actually haven't totally cured it because you still see okay, all true. But 1954 was what people would say because they could give a year. And again, it's not exactly accurate, but that's the common understanding of people in the street if they think at all. Now, let's go fast forward 100 years and say, when did we cure aging? When did we show we could literally reverse aging? Well, technically, I could say the answer is 1999. Okay, that's when we first showed we could reverse aging in human cells. In tissues, I'd say the year 2000. If we said the first human studies, I'd say, well, the first study came out in 2011. Okay, but if I were to go forward that 100 years and I go out and interview everybody in the street and I say, tell me the year that we first showed we could reverse human aging, the figure that people will give you will be sometime within the next decade.
So you're convinced it will happen or it might happen in the next decade?
Well, I'm convinced that it will happen, but I'm always a little, I know it can be done. Again, sort of internally, I have faith that we can do this because the theory fits together, the data fits together nicely, and we now are capable of doing this. But The BBC asked me a question like that a couple of years ago, and they said, how will you know if we do this? And I said, well, if I'm still alive at 150, I still won't be absolutely convinced it's not a placebo effect, but it's pretty likely that it's real. I think that we are there now. It's not a matter of velocity. It isn't. It's not a matter of creeping up on it bit by bit. And it's like trying to. If you looked at the figures on death for Ebola, you found that the figures, if the people were untreated, very high rate of death, up as high as the 90 percentiles in some cases, and down in some cases down in the 30% range with good ICU care. Okay, even lower in some minimal small samples. And those all had some effect, but the real effect, the sort of 90% versus 0% fatality rate, will be using immunization. And I think that pertains here too. If you're looking at altering our aging process or lengthening the healthy human lifespan, it's not going to be a matter of, well, we brought it up a year, we brought it up 6 months, we brought it up 9 months, we brought it up 2 years. No, there's going to be an inflection point. And that inflection point will come sometime in the next decade. And what we'll be showing is that whether you want to take it or not, whether there are side effects or not, whatever the cost is, we can actually reset the aging process dramatically, emphatically, significantly, and it'll be sometime in the next few years. It's not going to creep up on us. It's not a slow velocity change. It's a bang. It's like this change of Alzheimer's disease. No, it's not a matter of tilting it up a little bit. It's a matter of inflecting it and getting return of function.
I'm hoping very much that you will be correct, and I'm looking forward to that moment, that inflection point. Now, let's move on, however, and talk a little bit about, and I would ask you to tell us a little bit more about Telocyte, which is the biotech company that you just started last year.
Mm-hmm.
And how is that connected with that inflection point, perhaps?
Well, as I've already said, our intent is to go for the high-hanging fruit. We're not going to go for wrinkles. We're not going to go for skin aging. We're not going to go for osteoarthritis or osteoporosis or even vascular disease initially. We're going to start with our first project going for, sort of the impossible dream. We're going to show that we can prevent and cure cognitive decline in Alzheimer's disease and show that we get return of function. And let me be a little more specific about that, by the way, before I go into details too. Let's say I have somebody with very advanced Alzheimer's disease. They're in the nursing home. They can't feed themselves. They're very bad shape. Let me give a simplistic analogy. It's like saying in that patient, say that 90% of the neurons are dead, 10% are only damaged. The 10% that are damaged, we can probably get returned to full function. But I can't get back the 90% that are gone, okay? So there's sort of a Humpty Dumpty effect. Some things are gone, they're gone. If I look at moderate Alzheimer's disease, and again, these numbers are just made up. In moderate Alzheimer's disease, you might find that 10% of the neurons are dead, 90% are sick. The 90% that are sick, I can return to function. The 10% that are gone, I can't. So I'll get much better inflection, much better return of cognitive function if I have somebody with early or moderate Alzheimer's disease than I do with somebody with advanced Alzheimer's disease. So when I say that I think we can get return to function, I'm saying that both on theoretical basis of the clinical pathology, and the basis of the animal studies. So we think we can make a big inflection of that, but what's sort of completely dead is completely dead. It's like the old Princess Bride movie. There's a difference between mostly dead and completely dead. And mostly dead we can get back. Completely dead, not so much.
Very interesting. And so, how is your company going on so far? How is your fundraising and stuff like that?
It has dramatically gone through the roof in the past 2 weeks. And what happened was we had actually made no cold calls. We hadn't gone out and searched actually for funding because people kept calling us, but nobody committed to it. Example, there was a huge global mineral conglomerate that called, and they were interested in this. But then they turned us on to their business manager, and he didn't see it and never called back. That was the end of it. That's fine, their choice. But what we did was we finally went to the JP Morgan and the Biotech Showcase in San Francisco now last week. And I had some 48 meetings with different potential investors. Of those, about a third of the people were people who wanted money from us. That is, they wanted to do consulting or sell us a service. I appreciate that, but that wasn't our main function. And of the other 2/3, all of them, with maybe one exception, were interested in this. And so far we've had, as of today, I think 11 companies calling back saying, we'd like to talk to you about this. And even one who called out of the blue, wasn't part of that last week's group, who called me and said, I just finished reading your book twice. I said, why twice? He said, well, I liked it so much the first time, I wanted to go through the second time, make sure I really understood this. And they started talking about what we wanted to do. And what we are right now, we are officially looking for is a $5 million Series A equity investment, which is to say it's enough to get me through phase 1 human trials with Alzheimer's, and probably even through phase 2, which is an unusual statement for what's in biotech terms a small amount of money. But it has to do with what we're doing and how it should work. So we weren't asking for much in biotech terms, certainly more than I ever have in my wallet. How about you?
For sure.
But this person called and said, that's actually way too small an amount. We can probably bring it up substantially higher than that. And we can move on to other things as well as the Alzheimer's, all of which is interesting. So these discussions are going places.
That's very encouraging to hear. So can you perhaps give us an overview, sort of the bird's eye view of the roadmap, provided you do get the funding? What's your next steps?
Well, have you ever built a house and somebody says, well, when will it be built? When do you move in? When the walls go up and so on? And you've got an official timetable, but then there's a union strike and the weather gets bad and something doesn't get ordered in time. Okay, so there's your anticipated program and then there's reality. And sometimes they're both the same, but often reality does something a little different. If we have the money right now in escrow, if we had the money right now, it would be 6 weeks before we actually put in our first pre-IND meeting or ask for the first pre-IND meeting with the FDA. It would be 6 months before we finished any additional animal trials we need. And we could start the first Alzheimer's trial in fourth quarter of this year. We have an inpatient facility we can use, a researcher who's on our scientific advisory board who has done FDA-sponsored Alzheimer's research on an inpatient basis. And we have a number of places around the world that are interested in doing them, in Scotland, for example, Australia. So we're ready to go in a sense. So our program would be to begin the first 8 patients with therapy in the end of this year. We'd be probably able to finish phase 1, and this is an odd thing to say, but within 6 months. That's very unusual for an Alzheimer's trial because, again, we're looking at small changes over, say, an 8-year period. It takes a long time to get a baseline, but we're looking at rapid changes based on both theory and animal data. So we expect to see changes well within 6 months, which is an odd claim, but there it is. Even to claim that we can prevent and reverse Alzheimer's is an odd claim, but again, there it is. And we'd expect starting phase 2 next year. And with luck, we'd also end up with breakthrough therapy status, which would basically mean you can commercialize and begin to treat patients after phase 2 without waiting for phase 3. About 2/3, a little less, about 2/3 of applications for breakthrough therapy are turned down because they're not really breakthroughs. It's one more stat and one more small molecule. But it depends a lot on our phase 1 results. And there's pretty good chance, a priori, that we'd end up getting breakthrough status and be able to move on to commercialization and widespread treatment within 2 years. And again, that's optimistic, maybe unrealistic, but it's not based on guesswork. It's based on what we know about things so far. Now we'll see where things go wrong.
Mm-hmm. Let me give you a few more audience questions and start with one perhaps from Liz Parrish herself, because from the BioViva USA Twitter account.
Because I like Liz a lot.
And it's either herself personally or someone there. But anyway, she's asking, can you ask Michael what he thinks about glucosapine and if telomerase can help us remove it?
Now, I assume she wasn't asking glucosamine, but glucosapine?
Well, the way she spelled it is GLUCOSEPANE. So I don't know if I'm pronouncing it correctly. Glucosapine, or I'm not sure if I'm pronouncing it correctly.
No, I'd love to avoid embarrassing myself by going online and looking up glucosapine and seeing if it was something I actually knew something about, but I'll just confess ignorance and be honest about it. Glucosapine. I mean, I see the glucose molecule, I see the AIM part of it, but I'm not sure exactly where it is. All I can say is that everything we've looked at theoretically or in the lab so far, if you increase telomerase length, reset gene expression, you increase turnover and you begin to clear up a lot of problems. So, for example, if you're looking at cross-linked molecules, again, DNA damage, proteins outside and inside the cell, mitochondrial function, they all normalize. My guess would be the same, but I'll have to confess complete ignorance. No idea.
Mm-hmm. Well, let me ask you this from Steve Hill, which is kind of in the same realm. He says, telomerase has huge potential, but how can it prevent other damage that comes with age, such as, for example, and I'm not sure if I pronounce these correctly, but amyloids, lipofuscin, advanced glycation end products. These things jam up the cellular signaling environment and remodel the ECM. Can telomerase stop that?
Oh, yeah, it should. That's what goes on when you look at it in the lab. And if you look at actual animal responses, you get that same sort of answer. So let's take the example of advanced glycolysis, cross-links. I think I need a little less coffee or more. But if I'm looking at it, they're called AGEs. And if you're looking at things like that, like cross-linked molecules, the same problem that you saw with beta amyloid is going on in all these different pools. Amyloid, lipofuscin, all of these pools, they are dynamic pools. So if I'm looking at lipofuscin, for example, what happens is people are looking at it as a pool that's increasing in size, for example, and you're seeing these deposits laid down. But the real problem isn't the amount of time that goes by. The real problem is not the gene. The problem is the dynamic turnover, which is slowed down again. So, if we measure the cell's ability to deal with these sort of products, you'll see that the gene expression is turned down and they're no longer metabolizing or catabolizing the proteins or the molecules. So in all cases, these are not simply passive products. They're not static pools. They're dynamic pools. And what you've done as the cells age is you turn down the cell's ability to turn those pools over and essentially remove damage. So yeah, it all seems to improve nicely. Now, there may still be odd exceptions. For example, the question of turnover of lens proteins has been raised. Well, as it turns out, for decades, longer than that, people thought those protein pools were static too. It turns out they're dynamic. And if you look at the turnover of lens proteins, it also begins to go down with age. So I don't know what happens if we go into your cornea and into your lens and try to turn those up again. Do you find improvements in that? You should see an improvement in that, but does it make up for the fact that there's turnover very slowly, no matter how you do it? Or, for example, if you look at enamel on the teeth, the assumption has been you have a certain amount and that's all you get. Well, that's probably roughly speaking true, but what are the effects of telomerase on that? I don't know. There must be some pools that you can't improve enough to make much difference on, and others that clearly you can, as in the number of products that the person mentions, like fusions and age products and so forth, glycation products. All these things can be improved.
The next question coming from Brad Arnold is kind of continuing that line of investigation, but he starts like this. I sure would like to know why Aubrey de Grey poo-poos telomere lengthening. I would also like to know what Dr. Fossel thinks would happen if a human's telomere length remains above the critical length, i.e. about 1/4 the size at birth.
1/4 the size at birth. Well, I think I see where he's going. I'm not quite sure what he's asking, but let me just say this. We think we can return telomere lengths to essentially the lengths they were in cells in a young person. Now that includes, by the way, neurons. Most people realize that most neurons don't divide. They do, but not very much in the adult human being, for example. But nevertheless, the neurons in the adult neurons have shorter telomeres than they did when you were, for example, a fetus. Because again, there were continued divisions before your brain fully developed and neurons settled in place. And we can probably return those as well. In all cases, I think what we can do is return telomere length to essentially young normal lengths. But let me say that the young normal length doesn't matter. Telomere length is immaterial. Absolute telomere length is immaterial. What matters is relative telomere length. So, here the classic example is I look at certain varieties of mice, and you find that you and I may have telomere lengths, say, of 15 kilobase pairs in some relatively healthy, reasonable young cell. Say it was 15,000 base pairs. And maybe say it's 8,000 kilobase pairs in some cell that really isn't doing very well at all. Well, if I look at mice, I find that in some varieties of mice, you find a telomere length of 150,000 base pairs. Well, how can they have a short lifespan if they have a long telomere length? Well, it's because telomere length doesn't matter. what matters is change in telomere length. And even then, it's not the change that matters, it's the change in gene expression, the telomere position effect. So, in that mouse, they go from 150,000 base pairs down to 130,000 base pairs, still longer than yours and mine will ever be. But the point is that change in gene expression has occurred because of that. So there's a common misconception, particularly when people call it telomere theory of aging, that telomere length matters. No, relative length matters. Absolute length, completely irrelevant. And again, even if the telomere length were remarkably short, as long as the gene expression stayed the same, I wouldn't care. But there's no clear way to maintain a young cellular pattern of gene expression without increasing telomere length, which is why we do it, probably why the cell does it too. What was the question he asked before I went off on my rant about
why is it Aubrey always poo-poos telomere?
Oh, well, Aubrey has several misconceptions. And I'll leave it to Aubrey to try to talk about those. But let me give you an example of one. It's one that he and Judy Campisi have talked about at times. And I will put it in the context of, say, the knee, okay? Aubrey has suggested that if I were looking at, for example, a knee surface or skin or something like that, you have a certain number of senescent cells. And his suggestion would be, what we should do is kill off the senescent cells. And then you have a bunch of young cells, and so the tissue would work better. The problem is, this is like saying I have a whole group of people, some of whom aren't doing their work. They're working a little bit, but they're not doing their work. And so what we'll do is we'll fire them. And that means that the people who remain are going to have more work to do. Well, people remain are going to have to work harder because now you've taken away the people who are at least doing something. And in the case of cells, what happens is, let's say that I have 100 cells in my knee joint. And let's say that 20 of them were senescent, not doing their job. So we kill off the 20 cells. Well, that means the other 80 cells are now going to have to divide to replace the missing cells, in which case they become more senescent. So all you've done is replace some senescent cells with some other senescent cells. You haven't improved things. And in fact, you've increased the rate of aging of the knee as a whole. So there's a misconception about how the pathology works. Aubrey is not up to date, maybe, or pathology is not something he's knowledgeable about. We know that when we do this in animals, when we actually reset telomere length, not remove or kill senescent cells, but take the senescent cells and make the young cells again, we get better tissue function. So the data supports what we're talking about. Mm-hmm. I mean, I wish Aubrey well, but he's not thinking about the pathology well.
Mm-hmm. Mm-hmm. Well, Michael, I've been keeping you for a long time. So last audience question, and it's a big one, unfortunately, but maybe we can sum it up in a couple of points. Would be please from Martin Erickson, who says, please ask Dr. Fossel about CRISPR and gene therapy.
I think it's one of the most exciting things I've seen come along in years. But let me go back to that comment I made. We talked about earlier about the map versus the ship. Okay, if I have a really good map and I know how to sail from, say, Portugal to the New World, but I don't have a ship, it doesn't do any good. If I have an excellent ship but no concept of where I'm going, it doesn't do any good. You need both. CRISPR is not a map, but it's a heck of a ship. It gives us the ability, technically, probably, to do things we've been wanting to do for a long time and do them well. But what we've been talking about with regard to the last hour or so and telomere theory in general has to do with the map. And if you don't understand where you're going, you won't go some interesting places. Now, CRISPR will help. Let's say that I've got a patient with a known gene defect, something as simple as, or theoretically as simple as sickle cell disease. If I can go in and alter a gene in some kid, and I can fix that so the next generation doesn't inherit, or even fix it in the kid with sickle cell, perfect. But that doesn't take much of a map. I mean, that's a pretty simple map. We know what sickle cell is. It's a pretty simple disease in the genetic sense. In the clinical sense, it's a mess, but clinically, it's a pretty simple disease, not much of a map. The problem with aging is the map has been wrong. People have been sort of assuming it was a flat world rather than realizing it's round, or they've misplaced a couple of continents. And until we have the right map, you can't go very far with aging. I think CRISPR will have some effect on age-related diseases. It will have a much bigger effect on a lot of other, frankly, genetic diseases rather than epigenetic diseases.
Let me ask you this. What's the biggest misconception about aging?
The biggest misconception is that it's a passive accumulation of disease. And I'll put it bluntly. Most people think that damage causes aging. That is, you age simply because you slowly accumulate damage. Backwards. Wrong. It's not that damage causes aging. It's that aging permits damage to occur. If the cells are young, they stay up on repair, recycling, they repair the damage, the cell does well. Damage occurs, or accumulated damage occurs, because the cell's aging. So it's not that damage causes aging, it's that aging causes damage, in a sense.
Very interesting. And for those of our viewers and listeners who are interested in following your work and how it progresses, because it's very interesting and exciting, what's the best place for them to do that?
Well, they can go to my website, michael.fossel, michaelfossel.com. Thank you. michaelfossel.com. Okay.
I will link to it.
And take a look at some of the blogs, for example. I try to, every week or so, at least send out a tweet, which is becoming an old-fashioned way of doing things. I recognize that, but at least I put those out now and then. But it's hard to say much. Or you can keep an eye on the Telocyte website, which is just telocyte.com. And we will, I think, start progressing very rapidly in the next year.
I sure hope so. Dr.
Me too.
Fossel. So the last question that I always ask of my guests here is, what's the final message that you would like to impart on us? What's the most important thing?
Well, the analogy always comes to me with polio, because it's such a convenient one. You know, in 1950, people worried about the cost of polio and the cost of iron lungs and the cost of nursing care for children, and that it would bankrupt the healthcare system. Not an issue. It's, you know, the last person on iron lung died 2008 of parafailure, but there weren't many around. There aren't around. We don't worry about the nursing care costs. The same thing happens with regard to Alzheimer's. People right now are reasonably panicked about the long-term costs of nursing care and general care for Alzheimer's patients. It will become a non-problem. So there are lots of problems. You know, one is people don't think you can do anything about it. I think you can. People think that we're going to have terrible costs of Alzheimer's. I think we can get rid of those costs. And I think the best way to sum this up is, there's a quote I like from the Alzheimer's Association, or maybe I should say I don't like. They talk about, we need to learn how to live with Alzheimer's. No, I think we need to learn how to live without Alzheimer's.
We need to learn how to live without Alzheimer's.
Without, not with, without. It's not a matter of, well, let's just get used to it, suck it up. The answer is no, let's cure it.
Fantastic. And one quote that I like from the end of your book goes like this, by the way. The objective, quote, the objective of reversing aging is not to offer ears, but compassion, end of quote.
Yes. It's not just a matter of being able to cure the disease. It's a matter of caring enough to do it.
And you have revealed yourself twice now in a row during our interviews that, in my opinion, you're someone who deeply cares. And I sure wish you the very best of luck. Dr. Michael Fossel, thank you very much for being with us today.
Thank you, Nicola. Now let's see if we can do it.
If you guys enjoyed this show, you can help me make it better in a couple of ways. You can go and write a review on iTunes, or you can simply make a donation.
Singularity.